Hello. Uh, in the previous few videos, we are looking at the mechanical response of polymers. We mostly focused on the stiffness behavior of the polymers, saying that the stiffness depends on the temperature and the stiffness depends on the time. In this video, we will focus on the strength of polymers, meaning at the stresses at which it failed. Though stiffness is important, strength is equally important because it decides, uh, it plays a major role in the design of polymeric products. And during failure, sometimes we have failure is based on stiffness base, saying that okay, it should not deflate by more than so and so amount, but there are cases where more than flexibility or the stiffness, we are worried about whether the product will snap into two pieces or not. For example, like a laptop which has a plastic casing, right? It is okay if it is slightly flexible, but what is more crucially important for us is to ensure that it does not snap or break, because that will stop the functionality what it is intended to. So, in this video we will look at the different failure mechanisms by which these polymers fail and how it relates to other parameters. Okay. When we start about strength, usually strength is very less understood compared to the stiffness. So, our understanding of how the polymers deflect is much more than we know about how a particular polymer fails. For example, let us say any plastic product, usually there is a better understanding of how to manufacture them and how it behaves under a particular load. But if I have to predict at what stress it fails, it is very involved, because then we really need to understand several failure mechanisms, because these failure mechanisms compete with each other and the one with the weakest link fails. So, it is not just like you understand about one failure mechanism, but you should be aware of multiple failure mechanism and we should have mathematical description of it. Then we will be in a position to predict which is the failure load for a particular product. So, now we will look at different failure mechanisms. We will focus on mostly these four mechanisms, saying that the brittle fracture, cold drawing, shear banding and crazing. We will go into greater detail of each of it. So, let us start with brittle fracture. We already know that polymers fail in a brittle fashion when they are in a glassy state. This happens when the temperature is about less than 0.75 times the Tg. That is when the polymers are glassy and we expect this brittle behavior. So, usually these polymers will have low fracture toughness, meaning that the energy needed to fail is very less, and it can be estimated using techniques like the fracture mechanics approach can be applied to predict when does a particular plastic or a polymer fail under brittle fracture. But now let us see how this failure occurs. Usually it starts from cracks or notches. So, when the cracks or notches are present either on the surface or in the interior, these lead to stress concentrations, and once we have this stress concentration, the probability or the chances of the crack propagations are high, and that is how it fails. So, for example, here we have a small crack and we have seen that because of the stress concentration, this crack propagated and led to failure as shown here. So, it is important to ensure that at least on the surfaces the finishing is nice such that these surface imperfections are eliminated. This will avoid or minimize at least the brittle fracture. Now, let us look at cold drawing. Cold drawing happens because of large plastic deformation. This usually happens starts at least 50 degrees centigrade below the glass transition temperature. So, thermoplastics at these temperatures become plastic, or they show the plastic behavior. So, what we see is once loaded, initially it is linear, but around 0.1 it shows yield behavior. But beyond yield, what we see, this horizontal line or a large plateau is the drawing. So, usually these can go as much as 3%. So, as you can see, 3% is a lot for a material, because if you compare it with metals, it is usually much less than 1%. So, 3% is a lot of strain for a polymer, and we will see the molecular mechanism which lets this happen now. So, initially in this state, let us say this is one which is observed somewhere here. Now, we see that the polymer structure, depending on whether it is amorphous or crystalline. Amorphous means these are in a random shape, and if it is crystalline, these are neatly packed. But once we apply the load, let us see what happens. So, initially it starts to neck. So, at yielding there is a necking which is seen, which is now, let us say that this is 2 and this is somewhere here. So, necking happens in a local region where, because of higher stresses compared to the other places, the necking initiates. Necking meaning the cross section is smaller. Once the cross section is smaller and the load is the same, the stresses are high. Okay. But what happens in this necking? We now see that these polymeric chains are being stretched, means they are being aligned in the direction of the load. What happens when polymers align in the direction of the load? Previously we have seen it increases the stiffness and strength, which means this polymer in the necked region, they become strong. So, we are saying that after necking this region becomes strong. And now let us say we are still further loading. If we further load, it can do two things. One, wherever it is a neck, it further necks and fails, but that is not possible. The reason is because due to necking, the material already became stronger and stiffer. So, which means instead of this neck region, the other regions neck to the neck, that is where we have this stretching of the molecules happening. So, which means, so initially let us say it happened here, but after that it reaches a saturation point, meaning instead of deformation occurring there, it now occurs in the adjoining places. That is where the deformation happens and it keeps on drawing. So, let us say this is state 3, we are talking about somewhere in between. So, if we keep on increasing the load, what is happening now is this drawing or the necking extends throughout the length, because gradually all of these regions are becoming hard after necking, strong or hard after necking. So, that is why we say that this necking spreads throughout the specimen. So, usually somewhere slightly less than 3 is what we are talking about state 4, where it is reaching a complete necking. So, the necking has spread for the entire length of the specimen. So, when we said these chains have become straight, usually what happens is it unfolds for crystalline and it untangles the way it is shown in this figure for amorphous polymers. Okay. So, this is a operation where we have seen large plastic strains happening. Usually this is good for a polymer depending on the application. Let us say we are interested in preparing fibers such as nylons. So, usually people do this cold drawing process by which they get long fibers. Within the fibers, all these molecular chains are aligned along the length of the fiber. Because these are aligned, now these nylon fibers are very strong and stiff. Not just in fibers, but The same thing also happens in films. Now, if you are starting from a molten polymer and spread it across a surface, then usually what happens is these molecular chains are not perpendicular to the surface, but on the surface. So, since these are aligned in these directions, in the direction of the films or in the plane of the film, these are usually much stiffer. So, now let us discuss about crazing, which I think most of us have seen. So, usually when we look at cheap plastic and we crush a water bottle, or maybe we have seen some of the pens have shown some white streaks. Let us say when we bend it, it shows a white streak on it. We have also seen it on bottle caps and many other places. So, these white streaks are nothing but crazes. Now, let us see what is the molecular origin to this. This usually happens for high glass transition temperature polymers such as polystyrene. So, let us first see, this is a craze. So, we are saying small crack shaped regions which are called as craze, where we have these polymer which are drawn. So, we are talking about drawn polymers. Let us say this, what we show here are the drawn polymer. Drawn polymer meaning, compared to the surrounding molecular chains, these molecular chains are all aligned in one direction, but this only happens in a very localized region, not throughout the polymer, but in some specific region we have this crazing which is formed. But if we further load it, what happens is these drawn polymers chains, they snap and create what we now see as a crack. So, initially we have a craze region which is a white region. In this craze region we have these drawn polymer chains which are holding the top and bottom surface of this craze area. But when the loading is high, there is a snap at these drawn polymers. Once we have this snap, now a crack is created. Once there is a crack and there is continuous loading, what happens is this crack gradually propagates and then we have a longer crack. So, it starts with a micro scale phenomena and then ends up with a macro scale phenomena when the crack propagates. So, the crack starts from a craze and propagates, and which can lead to a complete failure in the product. So, usually let us say this is where the craze nucleates. And this is when the cracks start to form. So, this is this position 1 when the, let us say the craze nucleates, and this is when the cracks form and then the cracks eventually propagate. So, we will also see about this shear banding. Shear banding is another plastic behavior. The difference with crazing is this happens under compressive load. Crazing, as we have seen, happens when there is a tensile load, but for shear banding we are talking about compressive load. So, we are talking about large plastic strain under compression. So, this usually happens when there is a finite strain occurring at each shear band. So, these are the shear bands we are talking about. So, let us say we are talking about a material here which is shown here. Basically, we start compressing the material, but there is a position where the shear bands nucleate. What are shear bands? Shear bands are a local regions in the polymer where there is a shearing happening. Because of the shear, there is a plastic strain which is introduced in the polymer, but these are very local phenomena. But once you keep loading, or over time, when we have more and more of these shear bands like the things shown here, that is when the plastic strain accumulates and gives a large macroscopic deformation in the polymer. So, let us say this position is where the shear bands are more. So, there is the stresses which form shear banding are from these deviatoric stresses. What are deviatoric stresses? These are the stresses responsible for change in shape. So, these are shear stresses, something similar to. But dilatation stresses is what we have seen with crazing. Dilatation stresses are stresses which are responsible for change in the volume. So, volumetric expansion or compression is because of the dilatation stresses that leads to crazing. But for shear banding, we are talking about the stresses which lead to the shape, which are the deviatoric stresses. So, these are the differences between shear banding compared to the crazing what we see. So, until now we have seen these 4 mechanisms of failure, but let us see all in one diagram, which we will call this as the strength diagram of a polymer. So, first let us define what is the y axis. We are saying that it is strength. How do we define strength? We are now saying strength is when the material shows mostly nonlinear behavior, the stress at which it starts to show this nonlinear behavior. Let us say we are writing it in megapascals and the y axis in a log scale, meaning that there are large variations in the strength. On the x axis we have this normalized temperature T by Tg. So, let us look, as we increase the temperature, which of these failure mechanisms get activated. Initially we have this brittle failure happening at low temperatures, but as the temperature increases, the strength decreases, and eventually we see that there will be viscous flow, especially if we are talking about amorphous polymers. Initially their strength is high because they are in a glassy region where it is brittle behavior. So, until here we will have this brittle failure. But after this, depending on whether we are applying tension loads or compression loads, we will have crazing or shear bands. But if the temperatures are furthermore, cold drawing. So, when the temperatures are further low, we see cold drawing. And as we increase the temperature, we have the viscous flow. This diagram helps to see, depending on temperature, which of these failure mechanisms get activated. So, at low temperatures we are seeing this brittle failure, but at intermediate temperatures we either see crazing or shear bands, where essentially we are seeing plastic behavior. But as the temperature is slightly higher, we are now looking at cold drawing, where the deformations are much higher, and finally the polymer flows. So, we said low temperature lead to brittle failures, and as temperature increases, gradually we see crazing or shear yielding and later cold drawing. So, let us summarize what we have discussed in this video. We started by saying that strength is sometimes a design criteria depending on the application, but our understanding of the strength is not as much as our understanding on the stiffness. Nevertheless, we have looked into 4 different failure mechanisms, starting with brittle failures, which happen at lower temperatures when the polymer is in a glassy state, usually when temperatures are less than 0.75 of glass transition temperature. This is when the behavior, the toughness is low, and usually this is because of cracks and notches where we have stress concentration, and then once the cracks have enough stress concentration, they propagate and fail. So, later with cold drawing, we said usually for thermoplastics it is starting from 50 degrees below the Tg and above. So, usually in cold drawing there is a necking happening, and then this neck spreads throughout the length of the specimen. The reason for that is once necking happens, the molecular strains are aligned in the loading direction and then they become strong and stiff. So, under continuous load, instead of the necks, the surrounding areas start deforming, meaning in that regions the molecules align. So, later we have seen crazing is these white streaks usually we see on cheap plastics such as water bottle, pens and bottle caps. This is observed with high Tg polymers. There are crazed regions, the top and the bottom layer are connected by these drawn polymers. When these polymers are cut or snapped, that is when the crack is initiated. Under further loading, these cracks propagates and leads to complete failure. Shear banding, we said, is another mechanism by which the polymer takes plastic strain, but this is under compression stresses. We said these are under deviatoric stresses, meaning the change in the shape, the stresses responsible for the change in the shape lead to shear banding, whereas the stresses responsible to change in the volume, these are the dilatational stresses that lead to crazing. Though there are several other failure mechanisms, this being an introductory course, we are limiting ourselves to some basic failure mechanisms which we discussed. So, with this we conclude this video. Thanks for joining.